Hello, everyone. So today we're going to pick up pretty much where we left off last time, talking about the molecular orbitals of the hydrogen ion. So specifically, we're going to focus on a little bit more detail on the symmetric combination of the hydrogen orbitals, also known as the bonding orbitals for a hydrogen ion. So this is H2 plus, 1 electron, 2 protons. So last time we developed the fact that this state will have a wave function that is a combination of two hydrogen 1s electrons dampened by a normalization factor. So when we do this, we can go ahead and take the square of this function to give us back the probability density, and this will help us understand the shape, which we're going to refer to quite frequently as we start building up the energy of this system. So we have our normalization constant, which more or less will dampen the height of the whole thing, just to make sure that when we integrate it, it all comes back to 1. So we dealt with that last time. This time, we're going to deal with the three major portions. So this first portion is, again, going to be the density of electrons around atom A. So I've got two hydrogens. I'm going to refer to them as hydrogen A and hydrogen B. So hydrogen A will have its own certain electron density, which, because we have two identical atoms and a symmetric function, will be the same as the density of electrons on atom B. And these should trail off like we would normally expect for any sort of hydrogen wave function. But where things get a little bit weird is this intermediate region. So this is modified by our overlap integral, which can be thought of as a degree of enhanced density. So this is extra electrons that will pile up in between our two atoms, because you'll have electrons over here that say, ooh, another atom. I'm going to get a little closer. And electrons over here that say, ooh, other atom, and we'll get a little bit closer. So this is going to essentially pull away a little bit of the density from these two regions, causing them to go down a little bit. And that extra density will pile up here. So this is the reason why, as we increase our overlap integral, our n gets smaller, as I'm essentially dampening my two other peaks as the extra density accumulates here, again represented by twice the overlap integral. So what we're really going to be trying to look at is how I can describe the energy of this system. So we can think about breaking this into several parts. First, I've got the electrons around this atom that will be attracted to this atom. We've solved this problem before, but now what I have to figure out is how this electron density will be attracted to this atom and how this electron density will be attracted to this atom. And so we're going to do this by building up an equation. It is worth noting that you can also derive the same basic form by going the long way around and applying our Schrodinger equation we derived last time to our wave function. But for now, let's deal with our simplified form. So the energy of our bonding orbital can be represented by this equation. All right, there's a lot of terms here and only some of them probably look familiar. So let's start with the simplest one. So EH1s is going to be the energy of our hydrogen 1s orbital. So this is going to, again, represent, I'm looking at atom A, the attraction in between the electron density around atom A and that atom. So we know this energy fairly well. In fact, for 1s hydrogen, this is 1 Rydberg. Feel free to go back to the hydrogen atom if you want to review that. All right, so now I have to build in some other terms. So before I get to electron interactions, don't forget I still am going to have a repulsion between the two nuclei. So I can represent this repulsion via our classic friend, the interaction in between two elementary charges, because I've got two protons plus 1 charges. So they will have a repulsive or positive interaction based on the charges and how well this charge is communicated through a vacuum. But don't forget, it's also going to depend upon the distance between those two charges. our good old friend capital R, the distance between our two nuclei. So with that, it should hopefully make sense. We've got the energy of our electron around the 1s orbital as is, and then as I bring the other atom closer, I suffer a penalty or repulsion. But something has to bring that atom closer, and that's going to be our attractive term, which we break into 3 parts. So the first one is going to be this J term. So this is going to express the attractive interaction between this electron cloud around atom B. So this is our normal hydrogen 1s function, and this atom. So it's going to be looking at this attractive character. Then we also have to deal with the fact we have a little bit of extra electron density in this enhanced region. So this is going to be represented by our overlap integral, and we're looking at this extra attraction here. So this is going to be represented as K. So again, this is going to be how much I'm being stabilized by this extra near electron density and how attractive that is. Now this whole term is going to be an attractive term, thus a negative. So the more electrons I have over here, the more I'm going to stabilize the system. But don't forget, those electrons had to come from somewhere. I reduced some of my electron density here, but I did double the number of atoms. So using a little bit of technical trickage, we can essentially institute the normalization constant over here. Because again, 1 plus s is going to be related to the square of our normalization constant. So with some tricks, this ends up becoming a dampening factor on this attractive property. So we put this all together, and we're able to determine the energy of our bonding orbital. So this tackles the conceptual forms of each of these components. But us being P chemists, there has to be an equation for that. So we already know the equational form for these 3 variables, so let's focus in on these 3. And let's start with the one that really is defining the formation of a bond, that overlap integral. So I went ahead and promised that we look at this term, so let's go ahead and generate it. So again, the overlap integral is going to be the integral of the 1s hydrogen on A times the 1s hydrogen on B. Feel free to revisit this. It is going to be a dependence on the distance of our electron from atoms A times atom B. So doing some clever bits of trig, you can turn those distances from the electron to the atoms to actually being dependent on just the distance between the 2 atoms. And so with some clever manipulation, you can generate a polynomial expression which will dampen the, which will increase with radii. But don't forget, we need a dampening function because the further away these 2 atoms are, the less overlap between their orbitals, because lo and behold, electrons have a exponential die-off the further away they get from an atom. And so that's more or less where this term ends up coming from. And this is some of our classic integral magic, because guess what? We're working in a radial term with some extra nuance because of the trigonometric relation and a 3-body problem. But using this expression, we can generate our overlap integral. Then the next key term is looking at the interaction in between our electron on atom A and the nuclei atom B. So we're going to first need to co-opt our J naught, which again represents the electrostatic interaction between 2 elementary particles. Technically, this has to be modified by the distance, so you can imagine pulling this function in, and then we have a ratio of distance to charge. But we can pull it out, and all that's going to be left behind is, again, the wave function of the electron I care about, namely that on either one of the atoms. We're making heavy use of the fact this is a symmetric system. So we can then do the hard work of evaluating this integral, pull up a little bit of trigonometry, and we'll have a prefactoring prefactor term that's going to depend upon, again, our electrostatic energy and the distance between two atoms. So one can think of this as canceling out some of our repulsion in between the two nuclei. And again, this term is going to have a set value of 1 minus an exponential die-off. So if my radii is 0, this whole term is 1, and congratulations, I'm going to be equally attracted to the nuclei, to the other electron, as I'm being repulsed by the nuclei. It's a good thing we have an extra term here to cancel that out. But again, this will be dampened by our overlap integral. And if I have infinite separation, this term goes to 0, and we'll have a value of 1. So we'll have a value of 1, and this whole expression drops off. So hopefully that makes sense. The last term that we end up bringing in is K. So again, K is going to be our interaction in between the nuclei. For convenience, we're going to represent nuclei B, and the interaction between the two, between the overlap integral, again, wave function A and wave function B, and that nuclei. So again, we can generate an expression, and this time when we evaluate the integral, out front is going to pop the elementary electrostatic interaction in a per Bohr radii unit basis. And again, we're going to see a slight increase with radii at short distances, but overall, we're going to see a major die-off as the distances increase. And again, this should hopefully make sense, because as the distance between my two atoms increases, then lo and behold, I'm going to have less overlap integral to interact with, and in addition, it will be further away. So let's go ahead and look at this perhaps a little bit more visually, and it might help some of you there. So we can generate the expression for our overlap integral, and again, we will see a exponential decay, which is modeled for our two attractive energies, where they will also exhibit a form of decay, with all three of these becoming much less pronounced as our two atoms have gotten further away, and we return to just a hydrogen system. Because at this point, at infinite separation, the energy of the bond should be the energy of my starting orbital. So hopefully that makes sense. Now what we can do is take the first derivative of this equation and try and figure out what our minimum value is, because this will tell us a lot about our equilibrium bond length, when essentially these attractive terms are best able to overwhelm and dominate this original repulsive expression. So it turns out that this is going to happen at a radii, or a distance between my two nuclei, at about 2.5 of the Bohr radii. And this generates an overlap integral of 0.46. Please feel free to run through this math independently if you want to verify. We can also generate a attractive interaction with the new electrons on the other atom of about 0.4, and with the electrons in between the two in the bond of about 0.3. So one of the things that is worth noting is that as the distance increases, we're going to see this K value, or the favorable interaction with the bond, decrease at a much faster rate than the interaction with the other nuclei. And a good way to think about this is that the amount of electrons in that bond, in that overlap, are going to be dropping off at a pronounced rate, in addition to it becoming further away. So when we put this all together, it turns out that at this minimum energy, we will have the bond, or the bonding orbital, stabilized by about 1.76 eV over my original hydrogen electron. So one way to think about this is how stable I am in the bonding form versus that free non-bonding form, where I have my electron out by itself on a hydrogen atom. So congratulations, we just determined the bond energy of a hydrogen ion molecule. So that said, next time we're going to revisit the same process and look at some non-bonding orbitals and help compare and contrast between our bonding and our anti-bonding system. Take care and stay healthy.